Today we're going to explain address uniqueness in networking, what it means, how uniqueness is achieved, why it matters, the core features to understand, and the practical implications for network behavior. What is address uniqueness? At its simplest, address uniqueness means that each address used for routing or identification within a given scope refers to exactly one endpoint. When we say an address is unique, we mean there is no ambiguity. A packet sent to that address should reach one intended recipient. Uniqueness is a foundational assumption for routing, access control, logging, and monitoring. Without it, messages could be misdelivered, policies could be misapplied, and troubleshooting would be nearly impossible. How is address uniqueness achieved? The mechanisms differ by layer and by context. At the link layer, MAC addresses are intended to be globally unique, assigned by manufacturers and encoded into hardware. At the network layer, IP addressing uses hierarchical allocation and administrative control. Organizations are assigned prefixes and manage host assignments within those prefixes to avoid collisions. Dynamic assignment protocols like DHCP coordinate leases so two devices do not receive the same address at the same time. Interested in virtualized and overlay environments, controllers and orchestration systems maintain centralized registries to guarantee uniqueness inside the virtual address space. Address translation techniques like NAT intentionally collapse uniqueness at the public-facing layer while preserving distinctness internally. In all cases, uniqueness is enforced either by global standards, administrative control, or centralized coordination. Why does uniqueness matter? Uniqueness underpins reachability. Routers forward packets toward a single destination based on address. If two endpoints share an address in the same routing domain, packets may reach the wrong device or oscillate between targets. Uniqueness is critical for security and policy. Firewalls, access control lists, and audit logs rely on addresses to identify sources and targets. If addresses are ambiguous, accountability breaks down. Operationally, uniqueness simplifies debugging and capacity planning. When you see an address in logs, you can locate the corresponding device or service confidently. Finally, uniqueness supports performance optimizations like caching and session affinity. These depend on stable, exclusive mappings between address and endpoint. What are the key features and trade-offs associated with address uniqueness? First, uniqueness is scope-dependent. An address must be unique within the scope that uses it. A MAC should be unique on a local link. An IP should be unique within a routed domain or prefix. The same numeric address can be reused in different scopes. For example, the private IP 192.168 1.1 DEN can exist in many home networks without conflict because their scopes are isolated. Second, uniqueness can be static or dynamic. Static uniqueness is predictable but requires administrative effort. Dynamic uniqueness scales better but demands robust coordination and lease management. Third, uniqueness may be logical rather than physical. Virtual machines and containers are assigned unique addresses within an overlay, even as their physical hosts share infrastructure. Fourth, mechanisms exist to detect and resolve collisions. ARP probes, DHCP conflict detection, and controller-level checks prevent or remediate duplicate assignments. Fifth, uniqueness and privacy sometimes conflict. Technologies like MAC randomization intentionally break long-term uniqueness to protect privacy, requiring alternative ways to ensure reachability, such as temporary addresses or connection tracking. What are the practical implications for network behavior? First, collision detection and resolution add complexity and occasional transient disruptions. When a duplicate address appears, devices or controllers often withdraw the address, trigger reconfiguration, or block traffic until the conflict is resolved. Second, address reuse strategies and NAT affect end-to-end semantics. Collapsing many internal hosts behind a single public address preserves external uniqueness at the cost of obscuring internal identities. Third, monitoring and forensics must map ephemeral addresses to stable identities. When addresses change frequently, logs must correlate addresses with DHCP lease records, host names, or application identifiers to maintain meaningful traces. Fourth, high-scale environments require careful coordination. Cloud providers and large enterprises use hierarchical delegation, robust lease databases, and orchestration APIs to prevent collisions under massive churn. Fifth, security controls must be resilient to address spoofing. Uniqueness alone cannot prevent an attacker from forging addresses, so authentication and cryptographic identity are often layered on top of addressing. A few practical recommendations follow naturally. Use scope boundaries to allow safe address reuse where appropriate. Employ centralized assignment and tracking for dynamic environments to avoid split-brain collisions. Monitor lease utilization and enable conflict detection features such as DHCP conflict checks and RP inspection. For environments that require privacy, combine temporary address techniques with higher-level identity systems, so uniqueness for policy enforcement is preserved without sacrificing anonymity. And finally, remember that uniqueness is a design decision. Choose the approach that balances operational overhead, scale, security, and user privacy for your environment. Address uniqueness is not an abstract nicety. It is a working assumption that makes routing, access control, logging, and troubleshooting reliable. When uniqueness holds, networks behave predictably. When it breaks, misdelivery, policy errors, and opaque failures follow. Understanding how uniqueness is created, maintained, and sometimes intentionally relaxed is essential for designing networks that are both functional and resilient. That is address uniqueness.